Alright, so picking up where we left off, we've got our triangle, or our square here, our rectangle, and we found our uh, electric field in the x direction, net total. We found our electric field in the y direction, this direction. And so what we want to do is we want to find out what that total electric field is going to be, what this resultant is going to be. And so the way we do that is we have to actually use Pythagorean theorem on this guy. And so we end up doing that, and we can say that our E in the net, do that Pythagorean theorem, we end up with 88.2 newtons per coulomb. And now what we can actually do is we can find out what that angle is. And so if you need to have a picture, we go here, we go here. We know this one. This one is the 88.2. This one is our 52.4, and we want to find out what this angle is. The easiest way to do that is, actually, I like doing the tangent, but we could also do the cosine. So if we say that this is cosine inverse of the 52.4 divided by the 88.2 gives us an angle of 53.5 degrees above the normal, or 53.5 degrees. And so that, combined with this, is our final answer on number 6. Which brings me to question number 7. Alright, so number 7 is a little bit more in-depth, and there's a few things we have to understand about our problem. So we've got our palace, we've got windows, and these dimensions are on these windows. It's a 218 meter long window with a height of 50 meters. So we've got this big long rectangle. It's already been drawn for us, and so we have to find the electric field strength right here at the center of this rectangle. Now, one of the things we have to realize is that we have a force, or an electric field, from Q and from 2Q, and so it's pushing this one is pushing this way, and this one is pushing this way, and so those electric fields that are leaving those positive charges are actually going to cancel each other out. So how are they going to cancel? Well, what we have to do is we have to say that those charges are actually going to cancel, which means that this Q and this 2Q cancel out to be just a Q down here. So if we redraw our window, we've got our lines coming across, we got our lines coming across, we have a Q here, we have a Q here, we have a Q here, we have a Q here. This Q, this 1Q and this 2Q are going to cancel out, so we're left with just a Q down in that corner. And then this Q up here and these 3 Qs down here are going to cancel each other out, and so we're going to end up with 2Q down here at the bottom. Alright, so those Qs, those charges, those electric fields are working in opposite directions, which means that this one's got more more field than this one does. This one has more charge than this one does, and so it's going to cancel that out. So we actually have, in effect, no net field from these 2 points now, so we can just concentrate on these guys right here. Now, we also then need to find out what this theta is. We need to find out what this angle theta is. So let's look at angle theta. Well, angle theta, we know we've got this side and we've got this side, and so we can actually then find theta with that. And so we say that theta is equal to the inverse tangent of 50 over 218, which is 12.9 degrees. And so we've got that one. We can then also find out what our distance here is. And remember, the distance to this is actually half of this hypotenuse. And so if we find the distance there, that's going to be half the hypotenuse. And so let's go ahead and do that. Let's take our hypotenuse and find that with Pythagorean theorem. So we take the square root of 218 squared plus 50 squared, and then divide it by 2, and that gives us a distance of 112 meters. So this is 112 meters. This is 112 meters. So we've got that information now. So what do we need to do? We need to figure out what that field is right here at point E. And so we're going to look at this electric field here and this electric field here, see what direction it's going to go, and also what that field strength is. So how do we start that? Well, first we have to figure out what the strength of this, we'll call this Q1. And this is Q2. So let's find the electric field at 1. So we know that E is equal to K times 2. That's where this comes from. And our Q, we remember, is 6.4 nanocoulombs divided by our radius, which is this distance right here, which is the 112 meters squared. This is the electric field of 1. We can plug that in and we discover that this is 9.2 times 10 to the negative 3 newtons per coulomb. And what direction is that in? Well, that is in this direction right here, where that is a 12.9 degree angle. We have E2 now. And E2, we do the same thing. We've got K. We don't have a 2 now. We just have the 1Q. So that's 6.4 nanocoulombs divided by our 112 meters squared. It's a different direction this time. But we still have that. And it equals about half of that, 4.6 times 10 to the negative 3 newtons per coulomb. And it is in a different direction. It is coming this way with an angle of 12.9. So what we can do is we have to then divide each one of those into its component parts. And I'm going to have to move down because I'll need a little bit more space. So we have our E1. And so that one is going to be this direction right here. We have an X and we have a Y. And this E1 is going to be 9.2 times 10 to the negative 3. And that is newtons per coulomb. And this is a 12.9 degree angle. We have E2, which is this direction. This is also 12.9, and this is 4.6 times 10 to the negative 3 newtons per coulomb. So we want to find out what the X and the Y components of both of these are. So E1 to the X. Remember, the X is always a cosine, the Y is always a sine when we use this angle right here. So EX is going to be 9.2 times 10 to the negative 3 times a cosine of 12.9. E1 to the Y is going to be 9.2 times 10 to the negative 3 times sine of 12.9. That's going to be in this direction. That's going to be in this direction. And those are 9.0 times 10 to the negative 3. And this one is 2.1 times 10 to the negative 3. Now we find this one. We've got E1, E2 in the X. And E to the X is this one, and this is our angle, so that's also going to be the cosine. And so we say that it is 4.6 times 10 to the 3, that's the negative 3, times the sine, X is cosine, sorry, of 12.9. E2 to the X then becomes 4.5 times 10 to the negative 3. E to the y is going to be 4.6 times 10 to the negative 3 times the sine of 12.9. And that means that our E in the y direction is going to be 1.0 times 10 to the negative 3. And now we can add them all up together. We find our e to the x, and guess what? We've got two different directions here. Our e to the x in this one is going this way. Our e to the x in this one is going this way. And so what we have to do is we have to actually subtract those. So the e net in the x direction is equal to 9 to the negative third, e to the negative third, minus 4.6 e to the negative third. Sorry, 4.5 e to the negative third. That's my bad. And that gives us actually 4.5. And it is in this direction. We also have our e to the y. We can actually add those together because they're both in the same direction. And that becomes our 2.1 plus 1 is 3.1. And that is in the upward direction. And so we can use our Pythagorean theorem to find our net electric field in the up and right direction is actually going to be a 5.5 times 10 to the negative third newtons per coulomb. And the angle, we use the tangent of our x and our y. The tangent of our x and our y ends up being, sorry, this x ends up being 35 degrees above x. Hopefully that kind of clarifies some things for you guys. You can see it, you can watch it, you can see how I do these, and that should answer your questions. We'll talk about it in class.